Okay, so to start out, we'll talk a bit about exam number 2, how it is similar and different from exam number 1, and then we'll go into the outline of topics and key skills related to those topics from chapters 5 through 8. So exam 2 will be the same format and length as exam 1. There will be 20 multiple choice questions worth 3 points each. There will be 6 or 7 short answer questions worth the remainder of the 40 points. And now that we've started studying reactions, there will be some new types of short answer questions. There will be questions where you'll be given reactants and the reagents, the starting materials and the reagents, and then you'll have to predict the products of the reactions. And if there are stereocenters that are formed, you have to be able to correctly predict the stereochemistry of the products, much like our most recent quiz number 4. There will also be questions where you'll be given the starting materials and the products, and you will need to provide the reagents that will convert the starting materials into the products. And then there will be questions where you will have to draw mechanisms. You'll be given a reaction with the starting materials, the reagents, and the products, and then you have to draw the mechanism. When drawing mechanisms, there are a couple of important points to remember. Number 1, you don't want to skip or combine any of the steps. You want to make sure you draw each step out one at a time. And number 2, you want to be careful and precise in how you use curved arrows. A curved arrow shows the flow of a pair of electrons, and so it must originate at a pair of electrons. So each curved arrow that you draw has to begin at either a lone pair or a bond. It may not begin at a negative charge. A negative charge is not the same thing as a lone pair or a pair of electrons. A negative charge does not signify an individual pair of electrons. In fact, later on in the class, we will see molecules that have negative charges but do not have any lone pairs. So they're not the same thing. So we need to make sure that we have our curved arrows originating from a pair of electrons. And if you look at the mechanisms that I've drawn on the board in class, and if you look at the mechanisms in the book, they all follow this pattern. And one more thing is that for exam 2 and our subsequent exams, we are not going to have a sample exam online the same way that we did for exam 1. So the benefit, in my opinion, of a sample exam is that it allows you to see the format and length of the exam and to see the types of questions that you can expect. The disadvantage of a sample exam is that in my experience, it tends to make the students focus excessively on the questions from the sample exam and not on questions that may not have been on the sample exam. So in the past, when I've given sample exams and students encounter questions that are different from the ones on the sample exams, a high percentage of students will answer the question from the sample exam instead. And so to avoid those kinds of mistakes, we have a sample exam for the first exam, which is the one where you are not familiar with the length and format of the exam. But then now that you're aware of the types of questions, of the length of the exam and those sorts of things, there won't be any surprises in that regard. The best practice questions for the exam are the homework problems, as well as the questions that Preston and Alex are giving you in the recitations. Preston and Alex have access to a pool of exam quality questions. And so the questions that they're giving, as well as the questions in the homework, are going to be your best preparation for the exam. And they will help you to prepare more broadly and not to get the tunnel vision that students sometimes get if they focus too much on a sample exam. So all the types of short answer questions that I mentioned to you, namely predict the products, provide the reagents, and draw the mechanism, all of those are found in the homework problems in this section of the class. So working the homework, checking your answers and getting feedback on the homework, and participating in the Zoom recitations, those are going to be the best ways to prepare for this exam. The exam is the same length, but most students find exam number 2 more challenging than exam number 1. So the time that it takes might be a little bit longer. This exam 1, the average elapsed time was pretty close to an hour and a half. And on this one, the elapsed time might be more like an hour and 45 minutes or an hour and 50 minutes. So you probably want to allow yourself 15 to 20 extra minutes in the testing center when you plan your window of time to take this exam. Okay, so with that, let's go into. Sorry, lost my AirPod there. Did I put it in the right ear or did I put it in the wrong ear? That's why it fell out. It was in the wrong. Sorry about that. So we'll now go into our outline of the topics from chapters 5 through 8. So chapter 5 was entitled Stereochemistry. And in this chapter, we learned a lot of vocabulary terms and a lot of concepts related to the 3D structures of molecules. And so you need to understand these terms and you need to be able to apply these terms. So we started off with chiral, the definition of chiral objects, hands, baseball mitts, and so forth. And then we explained how to apply that definition to molecules. Molecules being chiral if they're non-superimposable on their mirror images. Then we learned about enantiomers. Enantiomers being stereoisomers that are non-superimposable on their mirror images. Then we learned the definition of a stereocenter. Our chiral molecules have one or more stereocenter. We learned how to identify stereocenters, and the process was a little bit different for acyclic molecules versus rings. So you need to be able to identify stereocenters in both acyclic compounds as well as in rings. Then we learned the RS nomenclature. So we learned how to assign priority. So that was kind of a subset of this topic, was the assigning priority for the 4 different groups at a stereocenter. And then once we have assigned priority, we should know how to determine that a stereocenter is R or S. Then we talked about compounds with more than one stereocenter. And there were a few things that we introduced with this particular topic. There was a formula for determining the maximum number of stereoisomers, the 2 to the n formula. There's very little math in this class, but you do need to be able to correctly use the 2 to the n formula. And then we learned about the definition of diastereomers. That's our catch-all category for stereoisomers. Any stereoisomers that are not enantiomers are going to be diastereomers of each other. And then we learned about mesocompounds. And remember, meso compounds are achiral molecules with stereocenters. And meso compounds will have a plane of symmetry. Okay. So being able to identify meso compounds, identify planes of symmetry, determining if molecules are chiral or achiral, determining relationships between compounds. Are they identical? Are they enantiomers? Are they diastereomers? These are all important skills related to these topics. And in the book, you'll find a couple of figures. Figures 5.10 and 5.11 are flowcharts that show the relationships of our different types of stereoisomers. I believe constitutional isomers are thrown in the figure as well. And then one of those figures shows us a flowchart of how to make a decision of the relationships between two compounds. So these are helpful figures that you can look at to review these topics. So we went on. In the latter half of the chapter, we studied the physical properties of our enantiomers. And we said that those physical properties were the same, except for two properties. The same except for the way they rotate plane polarized light. They rotate plane polarized light in opposite directions. Sorry, plane polarized light. And then we said that enantiomers will interact with other chiral molecules in a different fashion. So in regards to the rotation of plane polarized light, we had some vocabulary words that went along with that topic. We introduced the term optically pure. That's where we have a sample that is a single enantiomer, 100% of one enantiomer. Optically active. Optically active is where you have a mixture of the two enantiomers, but one is in excess of the other. And when we have an optically active sample, actually optically pure is a subset of optically active, I should mention that. We had the term percent enantiomeric excess, or percent EE, in which we take the percentage of the major enantiomer and subtract the percentage of the minor enantiomer to calculate that value. So these are all terms. We're not going to ask you to do these kinds of calculations, but these are all terms that you should be familiar with. And then we had the term racemic mixture. We've talked about racemization subsequently in the class, but racemic mixture also is a term that we need to understand in conjunction with the rotation of plane polarized light. And then one other aspect of physical properties, we mentioned that enantiomers have identical boiling points and melting points and solubility properties, but we did mention that the properties of a racemic mixture can be different from the properties of the individual enantiomers. We talked about how in a crystal, a racemic mixture will pack differently than an individual enantiomer. And there's an example in the book showing you different melting points for a racemic mixture versus optically pure samples of the individual enantiomers. So some subtle issues in regards to physical properties of enantiomers. And then point number 2 here, interactions with other chiral molecules. The examples we gave there began with the baseball mitts, where we showed that our left hand and our right hand will interact very differently with a single baseball mitt. We talked about the drug thalidomide, how one enantiomer interacts with proteins in the body in such a fashion as to provide relief from morning sickness, whereas the other enantiomer was tragically causing birth defects. Very different interactions with proteins and other chiral molecules in the body. And then there was the example of our nose. Our nasal our smell receptors in our nose are proteins that are chiral. They're present as a single enantiomer. And so different enantiomers of a molecule will interact with those receptors differently and give us different smells. I wish I could have passed around the bottles of Carvone so you could have smelled it yourself. But one smells like spearmint and the other smells like caraway. And then finally, in contrast to physical properties of enantiomers, with diastereomers, they have different physical properties. Diastereomers will have different melting points, different boiling points, different solubilities, and they may not differ by much. Sometimes they're similar, but there's no physical law that says they have to be the same, and they typically are different. Okay, so those are the topics for Chapter 5. So let's go ahead and erase the board, and then we'll discuss Chapter 6. And we don't have a big eraser in this room, so it will take me a little bit more time to erase this, so you'll just have to bear with me. Fast forward when you're watching this on YouTube while I'm erasing the board. All right. Chapter 6 is entitled Understanding Organic Reactions. And as I mentioned in class, understanding organic reactions is similar to understanding a foreign language. You don't ever completely understand them. But in this chapter, we learned some fundamental concepts that are helping us understand the reactions in chapters 7 and 8, and will help us with reactions that we will be learning in subsequent chapters as well. So we started out classifying reactions, the types of reactions, and I don't think you need to spend a huge amount of time in this section. Just make sure you can recognize and understand the reactions that we're learning in this section of the class, which would be the substitutions and eliminations. So if you can recognize substitutions and eliminations, then you should be in good shape. We talked about bond cleavage, the different ways that we can break bonds. And a key principle here is that bond cleavage requires energy. Okay. Formation of bonds is an energetically favorable process. Breaking bonds is unfavorable, so we have to put energy into a system in order to cleave bonds. We mentioned that there are two ways that bonds can be cleaved: homolysis or homolytic cleavage, where the two electrons in the bond go to different atoms. One goes to one and one goes to the other. And then we have heterolysis, where both electrons in the bond move to the same atom typically the more electronegative atom that is involved in the bond. So remember that there are different types of curved arrows that are shown or that are used to show homolysis and heterolysis. We use the half-headed arrows for homolysis. We use the regular curved arrows with the regular head to show heterolysis. So we need to make sure that we're using the proper curved arrows. When bond cleavage is performed, we obtain reactive intermediates. And there were three types of reactive intermediates that we mentioned. There's the radical, a species with an unpaired electron. There's the carbocation. And then there's the carbanion. So you should be able to recognize these species. The only one that we focused on really in this section of the class is the carbocation. So that's going to be the most important one for this part of the class. And then we had bond dissociation energy. Or BDE, defined as the amount of energy required to cleave a bond in a homolytic fashion. So it's important to remember that BDE refers to homolytic cleavage. So we talked about this in class. We mentioned that there are hydrogens that are more acidic, but they have a higher BDE, meaning that they're stronger bonds than bonds involving hydrogens that are less acidic. And that's because acid-base chemistry involves heterolytic cleavage. Bond dissociation energy refers to homolytic cleavage. So please do not spend any time memorizing numbers in terms of bond dissociation energies. Just being able to understand trends, being able to look at related types of bonds, different types of carbon-hydrogen bonds, different types of carbon or halogen bonds or hydrogen-halogen bonds, and being able to rank them in order of increasing or decreasing bond dissociation energy. That's much more important than memorizing numbers. So being able to identify the strongest bond out of a set of bonds or the weakest bond, that's the skill that you should be focusing on in terms of bond dissociation energy. So then we went into a discussion of thermodynamics and kinetics. Okay, so you should understand these terms. Thermodynamics referring to differences in energy between reactants and products, dealing with which side of an equilibrium is favored, and kinetics dealing with reaction rates, how fast those reactions occur. And the important thing to remember about these topics is that they are not related to each other, except in cases where Hammond's postulate tells us that they are related. Okay. So ordinarily, there's no connection between whether or not a reaction is thermodynamically favored and how fast that reaction occurs. So only in the cases where Hammond's postulate allows us to relate reaction rates and relative stabilities of products are they in fact related. So we went into reviewed some concepts related to thermodynamics that you learned in general chemistry. So the delta G formula, this is one that you're familiar with. We're not using it quantitatively in this class, just qualitatively to recognize the relationship between an equilibrium constant, and delta G values. Okay, and there was a table in the book that showed this relationship. So we just use this equation qualitatively in our class. We talked a bit about coupled reactions. This is something that you'll see in biochemistry, where the end goal is to accomplish a transformation that is not energetically favorable. And so in nature, that transformation is coupled to a process such as ATP hydrolysis that is energetically favorable. So being able to see how those are written with their own type of curved arrow and interpret them is the important skill in that case, as well as remembering that coupled reactions are not two different half reactions that are proceeding separately in a flask. We talked about the phosphorylation of glucose, and I said that glucose is not being phosphorylated by a free phosphate that gets generated by ATP hydrolysis. It's colliding directly with ATP, and ATP is transferring its phosphate. So please remember that the so-called half reactions of a coupled reaction are not really half reactions. We just split the reaction in half to understand the energetics. It's really one reaction and one reaction only that is occurring. Okay. So then we went on and we talked about entropy. And the key thing to remember with entropy is that a positive value for entropy is favorable. Having more entropy in the products than the reactants is going to be energetically favorable. And we said that in most organic reactions, changes in entropy are negligible. So we can usually set delta G equal to delta H, but there were two types of reactions where entropy was significant. Fragmentations. This is where we're splitting up. We have one starting material, and that fragments or breaks apart into two products. And that's going to have a positive delta S. That's going to be favorable in terms of entropy. And then we mentioned that cyclizations, where we take an acyclic molecule and we form a bond that generates a ring, that's going to give us a negative delta S and be energetically unfavorable. Okay, so remembering those two cases where entropy can be significant is important. Okay, then we learned about energy diagrams. And there is a lot of information contained in an energy diagram. So it's important for us to be able to read energy diagrams and get that information from them. An energy diagram can show us a transition state. We don't know what the structure of the transition state is, but we can infer what that structure would be. And we showed how to do that in class. We can get the value of the energy of activation off of an energy diagram. And remember that that is connected to the reaction rate, inversely proportional to the time it takes for a reaction, or to the reaction rate. Low energy of activation will have a fast reaction rate. A high energy of activation will lead to a low reaction rate. We can determine the number of steps in a reaction from an energy diagram. And we can also spot reactive intermediates. Reactive intermediates are local minima on the energy diagram. We can identify the rate determining step in a multi-step reaction. And then we can also measure the delta H. And each individual step will have a delta H and then we can measure a delta H for the reaction as a whole. So there's quite a bit of information that is available from an energy diagram. Okay. All right, then we finish the chapter off by talking about kinetics, the study of reaction rates. So we talked about how one can accelerate a reaction without using a catalyst. One can accelerate a reaction by increasing concentration and temperature. And we talked about why that increases reaction rates. And then we learned about rate equations, how to write a rate equation for a reaction. And along with this topic, we talked about the order of a reaction, how we can determine the overall order of a reaction. We can determine or of a step in a reaction, I should say, and we can determine the order of each step with respect to different reagents. So our SN2 reaction is second order. It's a single step process. It's first order in the alkyl halide and first order in the nucleophile. So being able to use that vocabulary is important. And then the last thing we talked about was catalysts. So you should know the definition of a catalyst. You should know how a catalyst accelerates a reaction by allowing a lower energy pathway, a different transition state. And then remembering that catalysts do not change the thermodynamics. A catalyst cannot make a reaction thermodynamically favorable. It simply allows us to reach equilibrium faster. And then in nature, our catalysts are enzymes, typically proteins. So those are the topics from chapter 6. So we'll go ahead and erase the board and then start with chapter 7. Thanks. If I'd been thinking ahead, I would have borrowed one of the big erasers from the rooms upstairs. Okay, chapter 7, alkyl halides and nucleophilic substitution. So in this chapter, we learned our first type of reaction, which there are two different mechanisms for. We had some vocabulary associated with alkyl halides. We have to be able to identify primary, secondary, and tertiary alkyl halides in order to understand their reactivity. There were a couple of other categories of alkyl halides that we learned. We learned about allylic halides as well as benzylic halides. And then there were the two classes of halides that are related to alkyl halides, but they are not alkyl halides, vinyl and aryl halides, which do not undergo nucleophilic substitution. And we explained why they don't participate in nucleophilic substitution reactions. We learned some nomenclature And the nomenclature of alkyl halides is quite straightforward. Very, very similar to the nomenclature we learned for alkanes and cycloalkanes. I should mention that on exam 2, as well as subsequent exams in the class, nomenclature will typically be tested in an indirect fashion, meaning you'll have less questions that are 100% nomenclature, but more questions where you have to understand the nomenclature and then use the result from that to solve a problem using a concept. So many of those problems use the names of compounds, and you have to be able to convert those names into structures in order to solve the problem. So you'll see nomenclature appear indirectly on exam 2 primarily. We talked quite a bit about interesting alkyl halides and the criteria for whether or not the information on interesting alkyl halides will appear on an exam is if we explained the function of an interesting molecule in terms of its structural features. And there was one alkyl halide where we did this, and that was Teflon. We spent some time talking about why Teflon is a non-stick substance. The very, very high electronegativity of fluorine causes it to hold on to its electrons so tightly that those electrons are not available for strong intermolecular attractive forces. Okay, so anytime we talk about an interesting molecule, understanding any cases where we can use structural features to explain the behavior or the use of that compound is where you would want to make sure you know that for a test. So then we started learning about the nucleophilic substitution reaction and some of the key components of a nucleophilic substitution. We spent some time talking about nucleophiles, and we divided them into two categories. We have our strong nucleophiles, and we said that those have negative charges, or ammonia counts as a strong nucleophile. Okay, and then our other neutral nucleophiles that are not ammonia are going to be weak, such as water or alcohols. We talked about leaving groups. We talked about what makes something a good leaving group. We said weaker bases are better leaving groups. We set a criteria for something to be a good leaving group. We said if the pKa of the conjugate acid is negative, if the pKa of that conjugate acid is less than 0, then that species is a good leaving group. So we have our halides, we have water. Those are the good leaving groups we've learned about so far. All of them have conjugate acids that are strong acids. Okay. Then we talked about two related concepts. I'll come over here for that. Nucleophilicity, and basicity. We said nucleophilicity is a kinetic property related to the reaction rate of a nucleophilic substitution, whereas basicity is a thermodynamic property related to the differences in energy between reactants and products. So these are sometimes related, but they don't have to be. We went over many cases in class where they are related, meaning that stronger bases are stronger nucleophiles. So we can say that these topics are correlated except for two cases: steric effects When we have a bulky nucleophile with steric hindrance, then that's going to be a poor nucleophile, even if it's a strong base. We had the comparison of tert butoxide with ethoxide in this particular case. And then we talked about polar protic solvents. And we said that in a polar protic solvent, we will have solvation of the nucleophile, and the smaller nucleophiles are solvated more efficiently, and that slows them down in their ability to function as nucleophiles. So these are our two cases where nucleophilicity and basicity are not correlated, where we can have species that are stronger bases being weaker nucleophiles. And then we learned about polar aprotic solvents. So being able to identify a solvent as protic versus aprotic is essential. And we learned that polar aprotic solvents are good for SN2 reactions because while they can solvate cations, they do not solvate anions, so they're not solvating our nucleophiles. Okay? All right, so at this point, we started studying the SN2 reaction. And there were a few different points that we learned in relation to the SN2 reaction. We learned that the 2 stands for second order. So it's a bimolecular process. Both reactants are participating in the rate determining step, and that was measured experimentally. The simplest mechanism that explains that is a single step mechanism. So that's the accepted mechanism for SN2. We learned about the stereochemistry of the SN2 reaction. It proceeds via inversion or backside attack. So you should be able to draw the products of an SN2 reaction, paying close attention to stereochemistry when that applies. And then we learned about the relative rates of SN2 reactions, wherein the less substituted alkyl halides react faster. So primary alkyl halides react faster than secondary, and our tertiary alkyl halides are unreactive in SN2 reactions. So the first 2 points come from experimental data. Those were empirically determined. And then the last 2 points, we did explain them. So it's important for you to understand why inversion or backside attack occurs and why our less substituted alkyl halides react faster. And then when we were talking about interesting SN2 reactions, the one we used to teach a principle was the mustard gas reaction, where we showed how mustard gas can cross-link the DNA. And the key lesson we learned from mustard gas is that SN2 reactions can occur in an intramolecular fashion. So if we have a nucleophile and a leaving group in the same molecule, they can react to form a ring. And we saw that in the intermediates that were formed in the mustard gas SN2 reaction. Okay. Then we went on and learned about the SN1 reaction. The SN1 reaction contrasts to SN2. The 1 stands for first order, meaning that only the alkyl halide is participating in the rate determining step. So it's a 2-step process. We have a carbocation intermediate that is formed in an SN1 reaction, and its formation is the rate determining step. The stereochemistry involves racemization And then we have an opposite order of more substituted alkyl halides reacting faster, opposite of what we saw with SN2. So much like with the SN2 reaction, we need to be able to explain these points, why a carbocation is formed. That comes from the rate data. Why that is the rate determining step or the slow step, why racemization occurs, and then why more substituted alkyl halides react faster in SN1 reactions. And that last point is related to carbocation stability. So remember, there are two concepts we use to explain why more substituted carbocations are more stable. We had inductive effects, and then we had hyperconjugation. Okay, so being able to explain why more substituted carbocations are more stable is important. Then we learned the Hammond postulate. And the Hammond postulate seems like it's just a common sense bit of information that a transition state will more closely resemble the species to which it is closer in energy. But the power of the Hammond postulate is it allows us to explain why more substituted carbocations are formed faster. It allows us to connect kinetics to thermodynamics in the case of endothermic reactions. So without the Hammond postulate, we would not be able to conclude that more stable products are formed faster in endothermic reactions. So it is very important, even though it seems like common sense. Then at the end of chapter 7, we compared and contrasted the SN1 and the SN2 reaction. So we looked at different factors in the reaction to help us decide or conclude whether a given reaction would proceed by SN1 or SN2. And the key thing to remember, well, we'll actually defer a lot of this discussion to the end of the review session, because I'm going to show you a flow chart that's going to help you decide if reactions are SN1 versus SN2. But the one thing I want to mention right now is that polar protic solvents are best for SN1. We talked about this in class on Friday, where the polar protic solvents can solvate both products of the rate determining step, the leaving group and the carbocation, and so they will accelerate SN1 reactions. And the polar aprotic solvents are going to be best for SN2 because there is no solvation of the nucleophile in the polar aprotic solvents. Okay, so this concludes chapter 7. So we'll have a little erase the board interlude and conclude with chapter 8. Okay, chapter 8, continuing on with alkyl halides, but discussing elimination reactions, the second characteristic reaction type. that alkyl halides will undergo. Since the product of elimination reactions is an alkene, we spent some time at the beginning of this chapter talking a little bit about alkenes. We'll have a chapter later on, I think it's chapter 10, where we'll learn more about alkenes. But at this point, we studied a little bit about their structure and how to classify them. We classify alkenes based on how many substituents are attached to the alkene and which carbon those substituents are on. Okay, so some of the key points in this discussion. We talked about how there's no rotation about the carbon-carbon double bond of an alkene. You should be able to explain why this is the case. The consequence of no rotation about the carbon-carbon double bond of an alkene is that we end up with cis and trans isomers, and these are diastereomers of each other. So being able to look at an alkene and determine if it can have cis and trans isomers is an important skill in this case, as well as being able to identify which one is cis and which one is trans. And then we talked about the relative stability of alkenes. And there were two factors there. We said that trans alkenes would be more stable than their cis isomers. And we referred to that as a steric effect. And then we also said that more substituted alkenes are more stable than less substituted alkenes. And we referred to that as an electronic effect. Okay, so recognizing more stable versus less stable alkenes, being able to explain why, those are the important skills in regards to that concept. Then we discussed the E2 mechanism of elimination. And of course, as with SN2, the 2 refers to the order of the reaction. So an E2 elimination reaction or dehydrohalogenation reaction is going to be a second order reaction where both the base and the alkyl halide are participating in the rate determining step. So that means that the E2 reaction is a concerted process. It proceeds in a single step. So these are topics we're going to, from here on out, these are topics we're going to cover on Monday and Wednesday. So these are ones that we haven't mentioned yet in class. So if you view this video before Monday, some of these topics might not be familiar to you. Strong bases are required in E2 reactions. And there are two special strong bases that we're going to learn about in class on Monday. And those are abbreviated as DBN and DBU. And it will be important for you to be able to explain why these are strong bases. And we'll go over that on Monday. We're also going to learn that more substituted alkyl halides will react faster in E2 reactions. Okay. And you'll need to be able to explain that concept as well. And then we're going to learn something called Zaitsev's rule. And Zaitsev's rule is related to something we did mention in class on Monday, which is that when we have more than, or on Friday we mentioned this, I'm sorry. When we have more than one type of beta hydrogen atom, we have the possibility of two different constitutional isomers being formed, or two or more. Sometimes you can have three types of beta hydrogens. And so Zaitsev's rule talks about or helps us to predict which of those constitutional isomers would be the major product. And there's a term we're going to learn in association with Zaitsev's rule, and that is the term regioselective. Regioselective refers to reactions in which more than one constitutional isomer is possible, but one of those isomers dominates. And then there's a related term, stereoselective, that we will also learn. A stereoselective reaction is one in which more than one stereoisomer is possible, but one is the major. So if we have the possibility of forming a cis or a transalkene, if one is favored over the other, then the reaction would be stereoselective. So then we're going to go on and discuss the E1 mechanism. And as is the case with our substitution reactions, the 1 is referring to the fact that this is a first order reaction. So that means it's going to be stepwise. That means only the alkyl halide is participating in that first step. And there's going to be a carbocation. The rate determining step of the E1 is going to be the same as the rate determining step of the SN1, as we will learn. E1 reactions require weak bases, so we'll talk about that. And we'll also learn that E1 and SN1 tend to occur simultaneously. Then after we finish discussing the E1 mechanism, we're going to talk about some geometry issues that are related to the E2 reaction. I'll just kind of list the terms now. It's hard to teach them to you without having taught them in class, but we're going to learn a term called anti-periplanar, which means that we need an anti-relationship between our proton and our leaving group. We know the term anti, we learned that in chapter 4, and we're going to learn how that applies to the E2 reaction. And the consequences of this anti-periplanar requirement for an E2 reaction are most apparent when we're using cyclic alkyl halides. And this is a topic that we're going to get to on Wednesday in class. And then also on Wednesday, we're going to talk about alkynes, species that have carbon-carbon triple bonds, a sigma bond, and 2 pi bonds. Those are going to be mentioned briefly in this chapter because they're formed via elimination reactions from alkyl halides, referred to as the double dehydrohalogenation. So if we have a dihalide and it can undergo 2 consecutive dehydrohalogenation reactions, then we end up with an alkyne. And a couple points that we'll teach that you will learn in relation to this is a stronger base is required than what you would use in a regular E2 reaction. So we'll learn some extra strong bases that can be used in this reaction. And then we'll learn about the types of dihalides. There's 2 terms we're going to learn, geminal and vicinal dihalides, 2 types of alkyl halides that will participate in these reactions. And then we will conclude chapter 8 with a discussion of our 4 mechanisms, SN2, SN1, E2, and E1, and being able to look at a given set of reactants and predict what products will form. So there's a flow chart that will be posted on Learning Suite that will guide us in making these decisions. And we'll just take a look at that flow chart now. We're going to go over it in more detail in class on Wednesday, but many of the principles that we would use for this flow chart we've already learned, so I'll just go ahead and introduce it to you right now. So the first thing to note is that vinyl or aryl halides will not participate in these reactions. So we have to have an alkyl halide to use the flow chart. And to be able to use the flow chart, we're going to have to categorize our nucleophile slash base. We have to be able to look at it and determine if it is a strong base or a weak base. And hydroxide is going to be our cutoff there. If it is comparable to or stronger as a base than hydroxide, it will be a strong base. If it's a weaker base than hydroxide, we would consider it a weak base. And then strong or weak nucleophile. Remember, we said that negatively charged nucleophiles or ammonia are strong nucleophiles, and the exception would be a bulky nucleophile, or a bulky species. So based on that, we can have four categories. We can have species that are weak bases and strong nucleophiles. The acetate ion is a classic example of that. The conjugate base of acetic acid is indeed a weak base, but it is a strong nucleophile. And then to be able to use this chart, we have to be able to classify our alkyl halides. We have methyl, primary, secondary, and tertiary. And then this will show you the outcomes, the reactions that will occur. So if we can classify our alkyl halides, and we can put our bases slash nucleophiles into one of these four categories: weak base, strong nucleophile, strong base, weak nucleophile. Tert butoxide is the one molecule we've studied that is in that category. Because of its steric hindrance, it is a weak nucleophile. Strong base, strong nucleophile. The alkoxides, the conjugate bases of alcohols, will fit in that category. And then down here we have our weak base, weak nucleophiles, such as water. So being able to put our reagents into one of these four categories, and then recognizing the types of alkyl halides we have, will allow us to predict the outcomes of reactions. Okay? And this is something I've said before, but with charts like this and many of the summary tables we have in the book, we don't want to just memorize the information in them. Rather, we want to understand it. So if you can look at this chart and you can understand why each of the different combinations proceeds by the reactions that are listed in this flowchart, if you can understand why and explain why to your study partner, then you will know that you have a good understanding of the concepts of substitution and elimination, and then you'll be ready to take the test. So that's all we have for our review session. I hope you are well prepared and will do well on the exam. Good luck.